Hello guys, chapter 15, section 3, thermochemical equations. In this lesson we will write the thermochemical equations for chemical reactions and other processes. We will calculate the heat absorbed or released in a chemical reaction, and we will describe how energy is lost or gained during changes of state. First of all, in the previous lesson we said that the heat absorbed or released can be measured using the calorimeter. Also, we defined the system and the surrounding. We said that the system is the part of the universe that we are studying. Everything else is the surrounding. System plus the surrounding makes the universe. And also, we said that we have endothermic and exothermic reactions. Moreover, we said that the enthalpy is the heat content of a substance, while we cannot measure the heat content of a substance. We can't measure the enthalpy. We can measure the change in the enthalpy, or we can call it the heat of the reaction. We said also that the endothermic reaction, they have a positive value for the delta H, while exothermic reactions, they have a negative value for the delta H. Now, these two equations, the first one for the heat pack, it's a heat pack equation. That second one is a cold pack equation. If you look at these two equations, you will find that these equations are balanced, and these equations, they include the amount of energy. Now here, because it is negative, we will know it's an exothermic reaction. This value here, it's a positive, so it's an endothermic reaction. Now, any equation, whatever is that equation, that includes, that's first it is balanced and includes the physical change states and the amount of energy or the energy change. If these two informations are included with balanced equation, we call it a thermochemical equation. So this and this, they are thermochemical equations. Take this example. H2 and I2 reacts to form 2HI. This reaction requires 53.2 kilojoules. Write the thermal equation of the reaction. So first, we know any equation, there is reactants and products. So H2 plus I2 produces HI. Now this reaction is balanced. When we write the delta H with it, this one they said it requires, so it absorbs energy. It's a positive value, kilojoules. If you wrote the reaction in this way, this is a thermochemical equation. We can write the energy in the reaction itself, but because it's an endothermic reaction, it comes with the reactants. If it's an exothermic reaction, we write with the products. So here we can write this equation like H2 plus I2 plus 53.2 kilojoules gives 2HI. These two ways are correct, and both of them are called thermochemical equation. It's so important to know that when it requires, so it's an endothermic reaction. So it's with the reactants. The energy will be added to the reactants. In exothermic, the energy will be with the products, and delta H will be a negative value. Now, any thermochemical equation, it also follows the stoichiometric ratios. So here, the overall reaction in a hot pack is 4Fe plus 3O2 gives 2Fe2O3. Delta H is negative 1652 kilojoule. They are asking how much heat is released when 2.5 moles react with excess of oxygen. So they specify the amount of moles that are used. In the reaction, based on the reaction, 4 moles of Fe reacts to produce negative 1652 kilojoule. This is based on the chemical equation. The delta H follows the stoichiometric ratio, so we can write in this form. The given here is 2.5 moles. How much energy we will produce? So x, just a ratio, solve the ratio. X will be equals to negative 842.4 kilojoules. Again, any chemical reaction that is a thermochemical reaction, it follows the stoichiometric ratios, and we are able to use the mole ratio to find the delta H produced or released, whatever is the amount of mole used. Now, a special kind of chemical reactions is the combustion reaction. You have to memorize the definition. A combustion reaction is a chemical reaction in which a substance, usually a fuel, that reacts with oxygen, releasing energy in the form of heat and light. So all combustion reactions, they are exothermic reaction. One of the reactants should be oxygen. Here we have a very famous example, which is the combustion of glucose. Your cells, they break down glucose in the process of cellular respiration, and the breaking down of 1 mole of glucose produces negative 2,808 kilojoules. Don't forget the negative means it's an exothermic reaction. Now, the amount of heat produced, by 1 mole of a substance is called the heat of combustion. The heat of combustion is the amount of energy released after burning 1 mole of that substance. As you know, the calorimeter is used to measure this amount. For the combustion of any substance, we can use the calorimeter. The bomb calorimeter is used in this case. These are 2 other examples of combustion reaction. For example, the methane, combustion of methane. Look at here, we have oxygen. It produces carbon dioxide and water. The amount of energy produced is 891 kilojoule. While here 1 mole, here also 1 mole. 1 mole of C8H18, which is the octane, it produces 5,471 kilojoule. So let us calculate the amount of energy produced if you don't have 1 mole. If you have more or less. In this case, how much heat is evolved when 54 grams of glucose is burned according to the equation? So this is the combustion of glucose, and as we said, this is the amount of energy produced by 1 mole of glucose. Here the given is mass. I have the mass of glucose. To find the amount of energy produced, I should convert it into moles. Then I use the mole ratio. So the number of moles equals the mass over the molar mass, which is 54 divided by the molar mass of glucose. In this case is 180. If you divide them, the answer will be 0.3 mole. 0.3 moles. So after converting the mass into moles, we can use the mole ratios to find the unknown. So based on the question, 1 mole of glucose produces this amount of energy. Okay? So how much energy is produced if I have just 0.3, much less than 1? The answer will be X will be equals to negative 842.4 kilojoules. Now, many processes other than chemical reactions absorb or release heat. Not only chemical reactions. Physical changes do that, the change in state. So, all of you guys, you know that we have the 3 most common state of matter are solid, liquid, and gas. Changing a solid into a liquid is called melting. Changing a liquid into a gas is called vaporization. It's so important to know that in this direction, from solid to liquid and from liquid to gas, we are heating up. On the other hand, if you have a gas, if you cool it down, if it releases energy, if it's an exothermic process, it's called condensation. From liquid to solid, it's called freezing. Now, let's start with melting and vaporization. The amount of energy required to melt 1 mole of a certain substance is called the molar heat of fusion, while the amount of heat required to vaporize 1 mole of a substance is called molar enthalpy of vaporization. What about these two values? By the way, guys, they are positive. The value of this one and this one is positive because both of them, they are endothermic reaction. The solid should absorb energy to melt, and the liquid should absorb energy to vaporize. Now, what about the others? Well, sorry, we can write this also as an equation. Vaporization of water and melting of ice. If you have liquid water, change it into a gas, the amount of energy required is 40.7 kilojoule. If you have solid ice, to convert it into a liquid, you have also to heat up. So the amount of energy required to melt 1 mole, just 1 mole is 6.01 kilojoule. Keep in your mind that the solid should be at its melting point. Here the liquid should be at its boiling point. Now, what happened in the reverse processes? When the water vapor condenses or when the liquid water freezes? Actually, the same amount of energy is required, but we write a negative next to them because they are exothermic processes. So the molar heat of vaporization is equal to molar heat of condensation, but they have opposite signs. The same thing here. The molar heat of fusion is equal to the molar heat of solidification, but with a negative sign. So these two are endothermic, so they have a positive signs, while molar heat of condensation and solidification, they are exothermic processes, so they have a negative sign. This table shows the difference, the different delta H vaporization, or the molar heat of vaporization for different substances. The same thing for fusion. If I want here to write the delta H of solidification, what will be the value for water? We said the fusion equal negative that of solidification. So 6.01 will be negative 6.01. The same numeral value but different sign. That for ethanol will be negative 4.94. How much energy is a cube of ice need to melt into water of 0.5 degrees Celsius, knowing that the cube has a temperature of negative 15 with mass 30, ice specific heat is 2.03, while water specific heat is 4.184. If we have this case, if we have a cube of ice, we want to melt it, but the ice is not at the melting point. So in this case, the first thing we have to do is to measure the amount of energy required to increase the temperature. This is called Q1. After that, we have to find the amount of energy required to melt the ice. So to change it from ice at 0 into water at 0. This is Q2. Then after that, the water temperature should increase to 0.5 degrees Celsius. This is Q3. So the first amount of energy, the first Q, we are changing the temperature. We are in the same state and changing the temperature. To find the Q will be equals to mc delta T. The mass given here is 30. The specific heat is 2.03, while delta T, if you subtract, T final is 0, T initial is negative 15, so it will be here positive 15. The answer will be 913.5 joules. Just to increase the temperature of ice from negative 15 into 0. Now, when the ice is at 0 and wants to melt, so we need the amount of energy needed, Q here, it doesn't depend on the temperature because the temperature is the same. So Q2 will be equal to the number of moles that we have times the molar heat of fusion. Because here we are melting the ice into water. Number of moles, we have to find it. They said we have 30 grams of ice. So number of moles equals the mass over the molar mass. So it's equal to 30 over the molar mass of water, H2O is 18. The answer will be 1.66 moles. So we have 1.66 moles. The molar heat of fusion, previously here we said the molar heat of fusion for the water is 6.01. We just 1.66 times 6010. Don't forget that value is in kilojoule. Here it's in joules. The answer will be 976.6 joules. After that, the water now it's at 0. The water temperature increased to 0.5. To find the amount of energy in Q3 required, Q3 will be equals to the mass of the water, which is the same like the ice. Mass doesn't change in any physical or chemical change. Mass times the specific heat of the water times the delta T. So mass is still 30. The specific heat of the water is 4.184 times the delta T, which is T final 0.5 minus T initial, which is 0. The answer will be 62.76 joules. So to find the total amount of energy needed to change an ice at -15 into water at 0.5, we add these three values. It's so important to know that the delta heat of fusion or vaporization or solidification or whatever, that for fusion, the substance should be at the melting point. If it's before the melting point, there is energy to heat it up to that melting point and the energy to melt it. The graph here allows us to understand the idea more. When you are heating up a certain solid, the amount of energy a solid absorbed, you use the formula Q equal mc delta T. When the solid reaches the melting point, the solid will melt. The amount of energy the solid absorbed to change into a liquid, we use the formula Q equals N times delta H of fusion. While when a liquid changes its temperature, Q equal mc delta T. But this C is the specific heat of the liquid, this C is the specific heat of the solid. Now, when the liquid reaches the boiling point, for the liquid to vaporize, the amount of energy to change from a liquid at the boiling point to a gas at the boiling point, Q equals the number of moles times delta H vaporization. And finally, if the temperature of the vapor increased above the boiling point, the amount of energy absorbed after that equaled mass mc delta T again. So to summarize, if the temperature is changing, use this formula mc delta T, but be careful which specific heat you are using. If the temperature is not changing, if the substance is at its melting point or boiling point, use the corresponding formula. Thank you guys for listening.